Hey my darlings, this is your beginning of Unit 4 video. This is going to be 4.1 through 4.4. Most of what we will be doing today is going to be the differences between physical and chemical changes. That is going to be mostly the new information. Everything else that you'll be seeing in this video is going to be a lot of review. So relax and get ready. The very first thing I want to show you is physical processes. What is very interesting about physical processes is it's just a change in intermolecular interaction. We've seen in the past, probably in some of your lower level classes, that physical process is a phase change. What's really interesting about physical processes is that there's a change in the intermolecular forces. In this case, in this example, from going from solid nitrogen monoxide to liquid nitrogen monoxide, you're seeing a change or a weakening in this intermolecular force. And when this intermolecular force weakens, it lengthens the distance between the each molecule lengthens, and that is why it becomes liquid. What's really interesting also is the composition of this molecule does not change at all. You still have nitrogen monoxide, and you have it in the same proportion in both the beginning and the end. Now, physical processes do not just happen when we have a phase change. Physical processes can also happen when we go from a liquid to an aqueous solution. In this particular case, we have this polar solute ammonia here, NH3, which is ammonia. What we have happening here is it is being dissolved, and well, not necessarily dissolved because it's not a solid, but it is going into solution in water. When it goes into solution, we actually have, again, a change in that intermolecular interaction. And we talked a little bit about these intermolecular interactions. When polar molecules are held in solution by these intermolecular forces, they actually change with these dipole right here. These hydrogens, and they're forming these hydrogen bonds here with these hydrogens. Okay, so the dissolving process is shown here. Again, we have exactly the same composition. It's still NH3. It doesn't actually change and show the water. What you show is just this aqueous right here. Okay, so you now have this NH3. This is your NH3 molecule right here, surrounded by water molecules, just like if this was an aqueous ion. Same concept. Okay, so where it gets really interesting, in my opinion anyway, is when we talk about chemical processes. This is where we have the breaking and the forming of chemical bonds. Substances are actually transformed into new substances, and they often have different properties. I want you to take a minute, especially write down some of the indications that a chemical change has occurred. You might want to go ahead and put those in your notes. I will not be reading those to you, but I do want you to put those in your notes. Here we have an example of a chemical process. We have sodium here, and we are going to combine it in a very simple synthesis reaction. We combine it with chlorine. We know individually here we have a metallic bond with our sodium, and our chlorine, of course, is going to be a covalent bond. Okay? We also know that chlorine on its own is actually a very foul-smelling poisonous gas. But when we combine it with this very soft metal of sodium, we get a very hard crystalline table salt. And table salt is ionic bonds. And we talked about in the last slide that the chemical process is the breaking and the formation of different bonds. Here we have broken a metallic bond. We've broken covalent bonds, and we have formed ionic bonds. We also know that this process is exothermic, which means that it gives off heat. It also gives off light. Those two things are indications that a chemical process has occurred. At the bottom here, we represent it in this very simple synthesis reaction, sodium plus chlorine, and we have sodium chloride. We're not worried about the different phases here. We're going to indicate them because that is definitely an AP skill. So we can indicate those processes, but what we want to show here is that the actual composition change from sodium plus a chlorine and we get sodium chloride. That is what is important in this particular representation. Now, interestingly enough, there is a little bit of a gray area because, you know, chemistry, we can't have everything be exact. Everything has to have these little exceptions to the rule. Dissolving a salt in water to become an aqueous salt in water actually involves both chemical and physical process. It involves both the breaking of the ionic bond. We have this ionic bond between sodium and chlorine, and it also involves the forming of ion dipole interactions. So our chemical process is going to be the breaking of this ionic bond. Then we also have the forming of these ion dipole interactions here. So we have a change in the intermolecular forces, which is a physical process. So we have both. This is a little bit of a, I wouldn't say a heated debate, but it is something that can be debated, and you can speak to both sides, that it could be both a chemical and a physical process. All right, so one other thing I want to talk about is the conservation of atoms in a chemical reaction. Okay, so this is just like when we talked about balancing equations. We want to have the same number of atoms on both sides. And I just want you to have the vocabulary correct when we talk about this. I want you to know that it is called conservation of atoms. So we must have the same number of hydrogens on both sides, the same number of oxygens, and the same number of carbons. This in particular is a CH4 plus O2, and it changes into CO2 plus H2O, and you should all hopefully remember that this is a combustion reaction, because anytime we have a hydrocarbon plus oxygen, we always get CO2 and H2O. So when you balance this out, you must have the same amount of hydrogens on both sides, the same amount of oxygens on both sides, and the same amount of carbons on both sides. That is the conservation of atoms in a reaction. You also will need to know that we have something called the conservation of mass. And I'm sure that you've heard that, but whatever mass you start with, in this particular case, started with 80.05 atomic mass units. And here all they did was add up the mass number, or the atomic mass of each element on each side, and we got 80. So let's say I started with 35 grams of CH4. I have to have, whatever I break that down to, I have to have the same amount broken down on the other side. So whatever that breaks down to when you do the math. Okay, so it's very important that whatever you start with, you must have at the end. So if I summed all this up and I had 176 grams, whatever I have on this side, it has to equal up to 176 grams. Hope y'all don't mind all my scribble scratch all over the screen. It's hard to erase on this thing. So, now balancing equations, you guys already know how to do that. There will be a little word bubble pop up that will show you that, just in case you need a little bit of review. And I'm going to show you one example of a net ionic equation, and I want you to make sure that you are able to do that. And again, a little word bubble will show up with a video in case you need to review that. Here's an example of balancing a chemical equation. I'm not going to go through it, just going through the screens. Here's an example of a net ionic equation. Very quickly, you're going to have to be able to do this from words. And here is the example. And again, there was a word bubble, or there will be a word bubble that will give you the video link to how to do this, so that you will have a little bit of a refresher on how to do this. And that is the end of this video. That is 4.1. Like I said, the easiest thing to do, guys, is to or the only new information you guys had on this particular one was that differences between chemical and physical processes. So I will see you in class tomorrow, and I hope you guys study up, because you know we're having like quizzes almost every day. See you guys later. Love ya.